the last video, we explored how to apply kinematics to rotation. Before we dive into rotational forces, we need to re-examine the concept of mass and see how rotation turns that into moment of inertia. Let's revisit Newton's first and second laws. They deal with forces. A force is simply a push or a pull. The first law states unbalanced forces cause acceleration, and the second law states total force equals mass times acceleration. If you have two objects of unequal mass and push equally hard on them, then according to Newton's second, the lighter one will have a larger acceleration, and the heavier one will have a smaller acceleration. This gives us an indication of the role of mass. If unbalanced force causes acceleration, mass measures resistance to acceleration. It describes how hard it is to accelerate an object. In the previous videos, we have seen rotational equivalents to displacement, velocity, and acceleration. We are now going to introduce the rotational equivalent of mass. It is called moment of inertia. In linear motion, mass tells you how hard it is to change an object's velocity. In rotational motion, moment of inertia tells you how hard it is to change an object's spin rate, how hard it is to cause angular acceleration. An object with a small moment of inertia is easy to start and stop spinning. An object with a large moment of inertia is much harder to start and stop spinning. Moment of inertia is symbolized by the capital letter I. Like mass, it is a scalar. But moment of inertia presents some subtleties that mass does not. Consider the skater. As she draws her arms in, her spin rate, her angular velocity, is increasing. In fact, her angular acceleration is increasing too. But how is this possible? Her mass isn't changing, so why should her angular acceleration increase? The answer is, moment of inertia does not just depend on mass, it also depends on shape. Even if mass is constant, it is harder to change the spin rate of a spread out shape than it is to change the spin rate of a compressed shape. And that isn't even all. The moment of inertia additionally depends on the axis of rotation. Here we see a wheel rotated about its center. It turns out that this has a different moment of inertia than this wheel, which is not rotated about its center. So to summarize, moment of inertia depends on mass, shape, and axis of rotation. Since it has to include both mass and distance, it is measured in kilogram meters squared. So now that we know what it is, how do we calculate it? Suppose you have a set of discrete objects, like asteroids, all rotating around a common point. Place the origin at the center of rotation and use this equation. In this equation, m is the mass of each object and x is its distance from the center of rotation. Multiply mass by the distance squared for each object and then add up all the products. Let's explore this in several examples. Here are two asteroids rotating about a common center. Let's calculate their moment of inertia. Consider this question. Two asteroids are in space. Both have masses of 10 kilograms. Find their moment of inertia around the origin if they are located at A, 2,0 and negative 2,0, and B, 4,0 and negative 4,0. I'm going to start this question by drawing the axes. There's x, there's y. There's 2 units, and there's negative 2 units. Now, we have two asteroids, one of them being 10 kilograms located at -2, and one of them being 10 kilograms located at +2. And here is the center of rotation. It's at the origin. It will be convenient to set the center of rotation at the origin for all moment of inertia calculations. Now, let's go ahead and let us solve for the moment of inertia of this system, how hard it is for these two to rotate about their common center. Moment of inertia is given as the sum of mass multiplied by the distance from the center of rotation squared. So in this case, because the center of rotation is at the origin, and because this is, we know what the position is, the distance is just going to be x. So we could write it like this. In this case, that's going to work out to mass of left times position of left squared plus mass of right times position of right squared. So, mass of left, 10, position of left, -2 squared, plus mass of right, 10, position of right, 2 squared. I know, by the way, the positions should have I hats after them, but because they're going to get squared, the I hat is going to go away. So this is going to work out to -2 squared is 4 times 10 is 40, plus 2 squared is 4 times 10 is 40. So the overall moment of inertia is 80 kilogram meters squared. So this is a relative measure of how difficult it is to rotate these two bodies, how difficult it is to, or what resistance they have to changes in rotation. So now that we've done it for when they are at 2 and -2, now let's do the second part of this question, which is what happens if they are located at 4 and -4. So one of them is located at -4, that's 10 kilogram. One of them is located at 4, which is the other 10 kilogram. Again, we use the same equation to solve for moment of inertia. Once again, that's going to be mass of the left times position of the left, or distance from the left one to the center of rotation, which is the origin, works out to the same thing, squared, plus mass of the right one multiplied by the distance from the right one to the center of rotation, which is again 4. So I'm going to, using basically the same equation as what we had before, that'll work out to I equals 10 times -4 squared plus 10 times 4 squared, which works out to -4 squared is positive 16. 16 times 10 is 160. And 4 squared is also 16, times 10 is again 160, which works out to 320 kilogram meters squared. So this is important. If the objects get further away, if you double the distance of the object from the center of mass, the difficulty of rotating it increases 4-fold. Double the distance from 2 to 4 and you quadruple the moment of inertia, and that makes sense because this is a square relationship you have going. If you triple the distance, it would be 9 times harder to rotate. If you multiply the distance by 4, it would be 16 times hard to rotate, and so forth. That's easy enough, but most objects around us have more complicated shapes, and you would need calculus to work out the moment of inertia for each one. Fortunately, your book has done the hard work for us. There's a table that lists the moment of inertia for several different shapes. If you know the dimensions of your shape and its axis of rotation, you can pick the correct equation and plug those values in. Consider this question. A thin rod has a length of 3 meters and a mass of 4 kilograms. It rotates around one end. What is its moment of inertia? In this case, we have a rod which is this long, which is hinged at one side. The rod has a length of 3 meters, so I'm going to represent that like this. And it has a mass of 4 kilograms. Let's say, to keep it simple, that it's going to rotate in the positive direction, that's counterclockwise. Now, we have been asked to find what is the moment of inertia of this rod. Now, if you had not been given any advice on this, you would have to use calculus to solve this out. Fortunately for us, the table that I showed just a few moments ago has that information. The moment of inertia for a rod like this, a continuous rod which is being rotated around one end, is given as follows. It's equal to the mass of the rod multiplied by the length of the rod squared divided by 3. So that works out to mass 4, length 3, squared divided by 3. 3 squared is 9. 9 times 4 is 36. 36 divided by 3 gives us 12. So the answer is 12 kilogram meters squared. So thanks to this shortcut, which your book has provided, we can easily find the moment of inertia for several different shapes, of which a rod that is rotating around a point, sort of like the minute hand on a clock or a watch, we can easily find out what its moment of inertia would be. We can expand this analysis to more complex shapes by breaking them into simpler ones. Consider this question. A windmill has 3 blades. The blades are attached at their ends to a central shaft. Each blade is a thin rod that has a length of 3 meters and a mass of 4 kilograms. What is the overall moment of inertia? I'm going to start by drawing my axes like this. The shaft of the windmill will be located at the origin. That's the point around which the blades will rotate. One blade I'll draw like this. One blade I will draw like this. And one blade I will draw like this. Each of these blades is 3 meters long and has a mass of 4 kilograms. So L equals 3 meters, mass equals 4 kilograms. And we want to find out what the total moment of inertia of this entire shape is. Now, fortunately for us, whenever we have a complex shape like this, we can break it down into simpler shapes. Each one of these blades is identical to this rod that we just solved for a few minutes ago. So the total moment of inertia is going to be given by the moment of inertia for the first blade plus the moment of inertia for the second blade plus the moment of inertia for the third blade. Each one of these blades, like I said, is identical to this rod, so that means that its moment of inertia is going to be 12. Therefore, the total moment of inertia for this set of blades for this windmill is 36 kilogram meters squared. My 101 students can skip the rest of this video. My 103 students should watch the rest. Although the book provides equations for different geometries, my 103 students should know how to calculate the moment of inertia of a continuous object. We set the origin at the center of rotation and then solve this integral. In this formula, rho is the density of the object and A of x is the cross-section area of the object. These variables should look familiar. We did something similar a few videos ago in center of mass. Now, let's apply this equation to some examples. A thin rod is 3 meters long. It has a uniform cross-section area of 0.2 meters squared and a uniform density of 5 kilograms per meter cubed. It rotates about its center of mass around an axis perpendicular to its length. What is its moment of inertia? Let's start by drawing the rod. And then drawing the axes. I'm going to set my axes like this, and I will explain why in just a second. This rod is going to rotate kind of like this. That is counterclockwise, as seen from over here, and it's going to rotate around its center of mass. Now, if you're not sure why this point over here, exactly midway down the length of the rod, is the center of mass, please go and revisit the video I did on center of mass a couple of videos ago. That explains a question which is very similar to this. Now, let's see what we were told. The overall length of this rod is 3 meters. That means that it is in this configuration extending from negative 1.5 on the x-axis to 1.5 on the other side. Now, if we were to take a slice, an infinitesimal slice of this rod, it might look something like this. The length of this slice is dx. The area of this slice was given to us. The area is equal to 0.2 meters squared. And the density of this overall rod was given as 5 kilograms per meter cubed. Now, let us start applying our equation for moment of inertia. Moment of inertia is equal to the integral of density times x over here stands for the distance between our infinitesimal slice and the center of rotation. But since we put the center of rotation at the origin, that means that we're really just looking at the position of that infinitesimal slice. That gets squared. Multiplied by the cross-section area of the slice, that's A, dx. Now let's plug in everything that we know. This is now the integral from negative 1.5 to 1.5 of the density, rho, x squared. A of x is 0.2, dx. So let's simplify this. 5 times 0.2 is 1. So this whole integral simplifies down to negative 1.5 to 1.5 x squared dx. And the integral of that is 1/3 x cubed. And that has to be evaluated from negative 1.5 to positive 1.5. Let's go ahead and do that. 1.5 cubed is 3.375, and 1/3 of that is 1.125. Minus negative 1.5 raised to the third power, which I will write like this, which is the correct way to do it on this calculator, gives us negative 3.375. Divided by 3, we get negative 1.125. (1.125) minus negative 1.125 gives us 2.25 kilograms meters squared. So this is the moment of inertia of this rod. This is the relative measure of how difficult it is to set this rotating. And we can confirm this value using the formula that was given in the book. Let's try it out. Now, in the formula, moment of inertia is given for a thin rod which is rotating around its center of mass like this, is equal to the mass of the rod multiplied by the length of the rod squared divided by 12. Now, what about the mass of the rod? How do we find that? Well, mass is equal to density multiplied by volume. So let's start by writing it like that. Density times volume times the length squared over 12. Okay. Now, we know the density, that's easy enough, but the volume is not yet known. So how do we find that? Well, volume is equal to cross-section area multiplied by length. So this now becomes density times cross-section area times length, all multiplied by length squared divided by 12. Now let's substitute everything in. That's equal to 5 times AX, which is 0.2, times length, which is 3 meters, times length squared, which is 3 squared, all divided by 12. So 5 times 0.2 times 3 squared is 27, divided by 12 is 2.25. That's exactly what we got before. So now we have confirmed what we originally solved using direct integration using the formula that was present in the book. For the object to rotate about a point that isn't the center of mass, it has to be hinged there. In these cases, we again place the origin at the center of rotation of the object. Consider this example. A thin rod is 3 meters long. It has a uniform cross-section area of 0.2 meters squared and a uniform density of 5 kilograms per meter cubed. It rotates about a point 1 meter from its end, around an axis perpendicular to its length. What is its moment of inertia? In this question, we have the same rod as before, but with one major difference. In this version, the rod is not going to be rotated around its center of mass. It's going to be located around a point somewhere to the left of that center. So I'm going to set my origin at the new center of rotation. There's X, there's Y, and here is the center of rotation. Now, a lot of the other parameters of this question are exactly the same. The density remains 5 kilograms per meter cubed. The cross-section area is still 0.2 meters squared. The dx is still going to have the same characteristics as before. The only thing that changes is that now there is only 1 meter. The rod has been shifted rightwards, basically, so there's only 1 meter that is to the left of the center of mass, and it extends a full 2 meters out to the other side. So now that we have this information, we are now going to solve, using direct integration, what is the moment of inertia of the object in this configuration. And just to be absolutely clear, why don't I draw an infinitesimal slice again? So it's a very similar operation to before. One thing I will say is that There is no formula which is given in your book that corresponds to a rod which is rotating at a point slightly left of center. You have one for rotating around the center of mass. There isn't one for one which is rotating halfway down or a third of the way down, as we are in this case. So let us now start setting it up in the same way as before. It's exactly the same equation. I is equal to the integral of, the big thing which has changed is the endpoints, the limits of integration. Here we were stretching from negative 1.5 to positive 1.5. This time it's going to stretch from negative 1 to positive 2. The density is still 5. The x squared is still x squared because we're still measuring the distance from this infinitesimal slice to the center of rotation, but that's just the x-coordinate of the infinitesimal slice, multiplied by the cross-section area, which is 0.2 dx. So that's going to work out to 5 times 0.2, that cancels out, and that leaves us with integral from negative 1 to 2 of x squared dx, which works out to, again, 1/3 x cubed, ranging from negative 1.5 to positive 1.5. Sorry, this ranges from negative 1 to positive 2. Now, let's go ahead and solve for what that would be. One-third of x cubed, where x is negative 1, gives us negative 1/3, so that's the latter term. And 2 cubed is 8. 1/3 of that would be 8 over 3. So 2 cubed, 1/3 of that is 8 over 3, minus negative 1 cubed is negative 1. 1/3 of that is negative 1/3. So that works out to 9 over 3, which is equal to 3 kilogram meters squared. And this is the moment of inertia of the same rod being rotated not at the center of mass, but at some distance to the left of the center of mass. So the center of rotation has been moved so that it's only 1 meter away from the left end, and we get a bigger moment of inertia as a result. If an object isn't rotating around its center of mass, there's a powerful formula we can use to solve for the moment of inertia. It's called the parallel axis theorem, and it looks like this. In this equation, d represents the distance from the center of mass to the hinge point, the center of rotation. So, if you know the moment of inertia when the object revolves around the center of mass, just add the mass of the object times the distance from the center of mass to the hinge point squared. That will give you the new moment of inertia. Let's try it out on that last example. In this question, we are going to confirm that the moment of inertia of this rod being rotated around this point far from the center of mass is given by the parallel axis theorem. We should get the same result as we did when we used direct integration. The parallel axis theorem says that the moment of inertia for a point not at the center of mass is equal to moment of inertia at the center of mass plus the mass of the object times d squared. Now, what is d? d is the distance from the center of mass to the place where the rotation is actually occurring. Now, the center of mass is located 1.5 meters from either end. But this new center of rotation is at a different location. It's only 1 meter from this end. So the center of rotation is 0.5 meters away from the center of mass. The center of mass in this configuration would be located at 1.5 units from either end. That would be at 0.5. The center of rotation is at the origin. So that's going to be 0.5 of a meter from the center of mass to the center of rotation. So let's plug in what we know. The moment of inertia around the center of mass is 2.25 plus the mass. Now, mass we already worked out. It's equal to the density multiplied by the area multiplied by the length. And all of that gets multiplied by the distance from center of mass to center of rotation squared. Plug in what we know. 2.25 plus density, 5. Area, 0.2. Length, 3. D is 0.5, and that quantity gets squared. So 0.5, like I said, corresponds to center of mass to center of rotation. So let's go ahead and work this out. 5 times 0.2 is going to cancel because that's just going to be equal to 1. So we're left with 0.5 squared is 0.25 times 3 is going to be 2.25 plus 0.75, which works out to 3 kilogram meters squared. Exactly what we got through direct integration. So now we've shown that we get the same result using the parallel axis theorem as we did using direct integration for this condition where the rod was being rotated around a point that was not at the center of mass. In this video, we introduced the concept of moment of inertia, the resistance to changes in spin rate. It depends on mass, shape, and the location of the center of rotation. We saw how to solve it for many different shapes, and we saw the parallel axis theorem. In the next video, we will discuss forces in rotational motion.